Okay. Mm. Okay, can you see my screen? Is that showing correctly?
Yes, perfect.
Okay. Hello, everyone. Again, I'm sorry I was late. Uh, Time zones are confusing. Um, just even more so if you've studied the philosophy of time, or takes on a feeling of unreality and hard to pin down in this. The title of today's lecture is Physical Aspects of Black Hole Evaporation. That's a vague title for a vague lecture. I'm going to talk about a variety of different things which I find interesting and relevant to the topic of black hole thermodynamics. Um, I'm going to start with a discussion of staying classical and not immediately talking about Hawking radiation, and thinking about how we can make the field of black hole thermodynamics richer even before we get to Hawking's derivation of the eponymous radiation. And the reason I do that is because I think there's good grounds to treat black holes thermodynamically prior to the derivation. I don't think, as Bruno discussed in the previous lectures, if you demand that the null energy condition is obeyed, then you're not going to be able to conceptualize consistently a black hole radiating and obeying the area theorem, which is going to make the analogy break down. But if you, for quantum reasons, allow yourself to consider the possibility that the area theorem doesn't hold because the null energy condition doesn't hold, then even before you've derived Hawking radiation, there's reason to believe potentially that the analogy is richer. And the reason is because of the sort of processes I'm going to discuss. So I'll discuss mass extraction, so mass energy conversion by black holes, and the Penrose process. So I'll take some time going through the process. I'm going to look at, we have a notion of an efficiency of a work process for a classical black hole, which very much looks like standard thermodynamic behavior. I'll then give a very brief introduction to Hawking radiation. I'm sure lots of people took the QFT on curved spacetime course. And so what I'd like to do is just give a sketch and overview of Hawking's original derivation, just to give something of a different flavor to what was given in the other course, which is the algebraic approach. But again, I won't go into any detail. And then I'll talk about how we model black hole evaporation the most simple-minded modeling procedures in a semi-classical approximation, where you model it as a normal black body radiator, obeying the Stefan Boltzmann flux law. And then finally, give a few comments on black holes as thermodynamic bodies once they're Hawking radiating. So we see lovely things like their heat capacity, their they have phase structure, which is very typical of thermodynamic objects. And then we'll look at a nice thought experiment about how black hole thermodynamics can teach us about future physics. Lots of what I'm going to say is going to be somewhat superficial. I'm not going to go into loads of detail in lots of other stuff, but this is sort of a concluding lay of the land lecture now that we've got our laws of black hole mechanics. Okay, so let's get in. This is lecture 6, and physical aspects, black hole evaporation. But again, don't hold too much to that title. So let's think about mass energy conversion by a normal classical black hole. I mean, Bruno has already talked about this process basically, but I'll just go over it again because it'll set up the Penrose process nicely. So if we have a particle of mass m being lowered towards, lowered quasi-statically, I'll say what I mean by that in a moment, towards a black hole, a Schwarzschild black hole, then we know on the exterior there's going to be a time-like killing vector field, xi mu. And I'm going to use mu because we're going to use some coordinates. So we're going to go xi mu equals d by d v mu, where here we're using the ingoing Eddington-Finkelstein coordinate, where v equals t plus r rs log r over rs minus 1, where rs is the Schwarzschild radius. Okay, so this is going to induce a quantity where E equals minus m x mu. It's mu where x mu is a forward velocity. And that's going to be conserved along GeoD6. So this is sort of our conserved energy. And we'll call it the killing energy. So that's our killing energy. So now we'll consider a particle which we're going to hold at constant radius and theta and phi. And so it's just traveling along, it's traveling perpendicular to our killing vector field, our v coordinate. So our coordinates of v are theta, phi. And so our forward velocity x mu is going to be xi mu over the norm of xi. So our killing energy is just norm of xi times m. Now, the norm of this quantity is given by the Schwarzschild metric. There we go, g mu nu, psi nu to a half. It's going to be, I'm not going to write the Schwarzschild metric out, but it's 1 minus rs over r to the power of a half. This quantity vanishes on the event horizon. So if we're holding up our particle at this fixed distance, then our killing energy equals E equals 0, sorry, on the event horizon. And if we normalize our xi so that it equals 1, well, we don't know, it approaches 1 as we go to infinity, we get, this is confusing. At horizon, and then E equals m at infinity. So one obvious way to interpret this is that we're going to have to put m mass into our particle to pull it out from near the horizon out towards infinity, as Bruno discussed. But conversely, if we slowly lower it over the horizon, so it's basically always going along a killing vector field, this is what I mean by quasi-statically, then we can extract the mass m, the entire mass m, as work from as the particle falls. And then when we finally drop it over the horizon, its energy is 0. And so we don't add any mass to the black hole. So we're using a black hole to return the mass of the particle into work. So this is an energy conversion process. So it seems like a maximally efficient sort of way of turning a store of internal energy into work, which is sort of classic thermodynamics fodder. So now a far more interesting example of something like this is the Penrose process. First, I'm going to define an ergo region. An ergo region is a region of our space-time where our Killing vector field, which is defining our time translation symmetry, becomes space-like. So it's going to be time-like at infinity. That's how we're defining it, the stationarity of a space-time. It emits a time-like Killing vector field at infinity. But then as you move into the region where stuff's happening, that Killing vector field becomes space-like. So this happens in the interior of a Schwarzschild black hole. So your time-like Killing vector field, as you cross the horizon, it becomes null, and it becomes space-like in the interior of the Schwarzschild black hole over the event horizon. But we can have an ergo region in the exterior of a black hole if it's rotating. You can actually have an ergo region in the exterior of a rotating star, but it's unstable and decays. The ergo region of a curved black hole is stable. So let's look at how this works. Again, we're going to assume that the charge is equal to 0, and we've just got a Kerr rotating black hole. So the Kerr metric can be written in Boyer-Lindquist coordinates, which is t, r, theta, phi. And should I write it out? No, I'm not going to write it out. And the time-like Killing vector field is given by, in these coordinates, mu equals d by dt mu. Now, as we saw in lecture 3, the lecture I gave on the first law, the metric is singular at r equals r plus minus, which I defined in the previous lecture. But we're considering the ergo region in the exterior of the black hole, and these coordinates aren't singular in the exterior, so they're good enough for what we're going to do. So we're staying in the region where r is greater than r plus, so we're fine. Okay. The first term, because I do use this, was sin squared theta over sigma dt squared plus further terms, where A is equal to JH over M, where JH is the angular momentum. Sigma, that's a terrible sigma. R squared plus A squared cos squared theta, and delta equals R squared minus 2M R plus A squared. So we want to compute the norm of our Killing vector field to see where it becomes space-like. So we compute xi mu with GTT, which is equal to sigma, which if you plug all the numbers in, is 1 minus 2mr over r squared plus a squared cos squared theta. This is negative and thus time-like if r squared minus 2m plus r plus a squared cos squared theta is greater than 0, which is equivalent to r is greater than m plus m squared minus a squared cos squared theta, which means that our Killing vector field is space-like in the exterior in the region larger than the exterior horizon, so greater than this, but less than where we just proved that it's time-like, minus a squared cos squared. So we have our radius at which we have a space-like Killing vector field. This is going to be the ergo region or the ergosphere, and its surface is called the ergo surface. Hold on, my laptop's making noises, so I'm just going to mute that. I mean, clearly when theta equals 0 or pi, then this term vanishes. And so at the poles of our black hole, we don't have an ergo region. So if this is our black hole, the ergo region looks like that. Great. And so here we have a space-like Killing vector field. Now, if we often talk about stationary observers, which are observers moving along the integral curves of Killing vector fields. Now, if that's how we define a stationary observer, then a stationary observer can't follow an observer can't follow a space-like path. So in the ergo region, there's no such thing as a stationary observer. You can't follow the curves along which the space-time looks stationary. The interpretation of that means that the rotation of the black hole in the ergo region forces all observers to get dragged along with it. And so you can't be a still objective observer in the ergo region. You're being whirled around. So now let's use this ergo region to extract some energy from our black hole via the Penrose process. Okay, so again, we're going to have a particle of rest mass m and for velocity xa. I'm going to make that a bit bigger. We're gonna let it fall into our ergo region. Its killing energy again is going to be E equals minus m xa xia, and then with respect to a stationary observer at infinity, and its for momentum is going to be the mass times the for velocity. Now at some point here, let's call it Q, doesn't matter, in the ergo region, the particle is going to decay into two other particles. Let's call them 1 and 2. Now, we can apply the equivalence principle, which means at any point, so at Q, we can apply space-time Lux-Minkowski and we can apply special relativity, which means at Q, we know that the for momentum has to be conserved. So PA, our original for momentum, is going to be P1A plus P2A, where P1A and P2A are the for momenta corresponding to our two particles. P1. If we define EI as the contraction of the for velocity with the Killing vector field, I mean, this is just the killing energy for both particles, where I is indexing the particles. And then contracting this with our Killing vector field gives us E equals E1 plus E2. Simple energy conservation. Now, because xi is space-like in the ergo region, it is possible for the energy of one of the particles, let's pick 1, to be less than 0. So normally we define energy as bounded below. We don't let energies be negative. So what's going on here? Well, really, the way we define energy is with time translation symmetries. Time translation symmetries tell us what energy is. And now our time translation symmetry in the ergo region has become space-like. And so the associated conserved quantity, or energy, now behaves like a spatial momentum. And so whereas energy is bounded below, a spatial momentum, of course, can be negative. Pick a momentum in one, it's a vector. You pick a momentum in one direction, the opposite direction is negative. So now our definition of energy in the ergo region, i.e. the quantity that is the conserved quantity that's defined by our time translation symmetry, behaves like a spatial momentum and so can be negative. And so assuming that E1 is less than 0, we still need to conserve energy. So that means E2 can be E1 plus the norm, E plus the norm of E1, which is going to be greater than E. So if, going back to our diagram, I badly labeled it there, so I'll draw it again. So this is our ergo region. This is our black hole. Our particle has fallen in, and P1 goes this way, P2 goes this way. If P2 escapes from the black hole, then a particle is coming out of the ergo region with more energy than the one we originally sent in. So we've sent in a particle, we've got one back with more energy, we've gained energy from the black hole. In fact, it can be shown that the negative energy particle must fall into the black hole, which leads to the black hole losing mass energy. Thus, we have extracted mass energy from the black hole. The negative energy particle falls into the black hole, positive energy particle escapes. So the obvious question is, how much energy can we extract? So now recall that on the horizon, we have a killing vector field. Chi A plus Xi A plus omega H Psi A, where chi is a future-directed null horizon vector. And then off the horizon, it's going to be causal. And so we have a momenta, a form momenta contracted with, minus a form momenta contracted with chi A is going to be greater than 0. So if we just contract this killing vector field with PA, we get PA chi A equals PA here, this is E H L, sorry, the minus sign here, I think. Well, I might have lost some signs, but we're defining L as equal to psi A P A, which is the conserved angular momentum of the particle. So, I mean, you can double check my signs as we've gone through, but you end up, when you apply this, with E minus omega H L has to be positive. Which means that, of course, L is less than E over H, where we have where the angular velocity is positive by convention. So we just decide whichever way the black hole is spinning, that's positive angular momentum. Angular velocity, sorry. And so we can see that if, as we said, the energy of our particles across the event horizon is going to be negative, then also by this equation, the angular momentum has to be negative. So the particle must have angular momentum in the opposite direction to that of the black hole. And thus, as it crosses the event horizon, so it must reduce the angular velocity of the black hole. Now going up to our equation for the ergo region again, remember that A is J over M, so it's the angular velocity. So if you're reducing the angular momentum of the black hole, you're also reducing this A term. And so you're going to be shrinking the ergo region. And eventually, if you apply the Penrose process enough times, you're going to take away all the angular momentum from the black hole. So you can be a bit more precise. So I suppose after our particle has fallen in to the black hole, we let it settle back down to a stable Kerr solution with a slightly different mass, where the change in the mass is given by E, and the change in the angular velocity, angular momentum, is given by L. Thus, delta J is greater than, this is just our same equation from above, omega H, plugging in our angular velocity. I don't think at any point in these lectures I've derived this, but any book on general relativity will do that for you. So this is just our angular velocity at the event horizon, delta M. Good. Now define the irreducible mass, which is we label MIRR, as the square root of a half m squared plus square root of m to the 4 j squared. Okay. Now it's easy to show a couple of lines at home that if you just differentiate this and use this equation by plugging in, just do chain rule for this on dm and dj, you find that the change in the irreducible mass is greater than 0. So this tells us that in the Penrose process, the irreducible mass must increase. Inverting the definition, so let me write that down. In the Penrose process, irreducible mass must increase. So inverting our definition of the irreducible mass, we find m squared equals MIRR squared plus a half j squared over the irreducible mass squared. It's greater than or equal to the irreducible mass itself, because this term is positive semi-definite. Which tells us that the mass of the black hole must always be greater than the irreducible mass. And so we can't, what this tells us, because we have to increase the irreducible mass in the Penrose process, even though we can decrease the mass of the black hole in the Penrose process, we can't reduce it below the irreducible mass. Okay? Thus, assuming we start with a black hole of a particular mass, start with a of mass m0 and angular momentum j0. then if we assume that we saturate all these inequalities, we can get arbitrarily close to saturating them. So let's just say we saturate them, and so the irreducible mass, change in the irreducible mass is 0. You can't technically do this, but you can get arbitrarily close, so we say you can. Then we find that we can extract m minus the irreducible mass is given by the two initial mass, initial mass and our initial angular momentum, until the angular momentum becomes 0. Because, I mean, when the angular momentum is 0, you can see from this equation up here, when the angular momentum is 0, then the mass is just the irreducible mass, and we've sort of reached our limit, and the ergo region has vanished. So we extract this amount of energy, and then we've taken away all of the energy we can by the Penrose process. For a maximally rotating black hole, an initially maximally rotating black hole, where J0 equals m0 squared, m minus mir is approximately 29%. So you can extract about 29% of the energy from the black hole via the Penrose process, if we start with a maximally rotating black hole. So, I mean, the question you should now ask is, well, I'm extracting all this energy from the black hole. What about the area theorem? How is this consistent with what Bruno did in the previous 2 lectures? Well, if you recall from my lecture 3, consistency with delta A is greater than 0. We prove that for a Kerr black hole, the area is equal to 8 pi m squared m root m squared minus a squared, which means that A is equal to 16 pi times the irreducible mass squared. And so, given that we can't reduce the irreducible mass, we also can't reduce the area. And so the area theorem is perfectly safe. It can actually be shown, I certainly don't do it here, it's more complicated, but the area theorem implies that the energy extraction of 29% is the maximum for any process of energy extraction for a black hole where we're using sort of classical light processes, so not like Hawking effect and whatnot. So the Penrose process achieves the maximally efficient energy extraction, well, it can achieve the maximally efficient energy extraction from a black hole. It's also the upper limit of, for example, the energy that can be extracted in the form of gravitational waves when 2 black holes merge. It's also a wave theoretic analogy of the Penrose process called superradiance, where a wave is incident upon a rotating black hole and the reflected wave has more energy. And you can also extract energy from black hole by neutralizing it. If you have a charged black hole and throw a charge of the opposite polarity in, you can neutralize and extract energy that way.
Sorry, may I ask a question?
Mm-hmm.
Like, if you consider Carnot engine, so in efficiency of that Carnot engine, you say that this much of work we can convert into useful work, and rest of the goes into sink. So here, I mean, 29% is used to increase the energy of the particle. How about other energy, like rest of the energy? Where does that go?
So I didn't hear the second half of your question.
Like here, what is 29%? Is that efficiency to give energy to that particle?
No, it's not efficiency proper. It's just the ratio of how much of the mass of a maximally rotating black hole is extractable. How much of that energy can we get out? Different processes, but it's therefore related to efficiency because it's sort of like a maximal achievable work from a particular process. And so I don't want to say anything strong. I'd be wrong to say this is efficiency as it looks in like in a Carnot cycle. But you're not going to be able to be more efficient than you're not going to be able to extract any more energy than this. So there's a certain interpretation of it which looks a lot like efficiency.
Yes. Okay.
Thank you. So these classical processes look a lot, to my mind, like normal thermodynamic processes and reversible ones at that. Have strict energy conservation and even a heuristic notion of the inaccessible energy of a system, which is very analogous to the entropy of a system, right? So we have this relationship between, we know the area is closely related to the entropy, but also we've got now a physical interpretation of that in terms of the irreducible mass being the unavailable to us energy of a black hole, which is sort of what a measure of entropy is. If you have a highly entropic system, you can't do any work with it, or much less. However, a classical black hole is black, and in the sense that we don't believe it emits Hawking radiation, and so it has a temperature of 0 degrees Kelvin. And so the analogy is going to break down, as I said in the introduction. But we have to be careful about what we think we mean by a classical black hole. If I think about a quantum field theory on curved space-time paradigm, but I haven't derived Hawking radiation yet, then I know that black holes are going to be good models. But I also know I'm going to have quantum fields on my space-time. And if I expect them to be able to violate the null energy condition, then I also don't need to expect the energy theorem to hold. And so I can assign a black hole a temperature. I don't have a good motivation for that, but I don't have this knockdown argument against why the analogy in all the other forms has to break down. And therefore, I mean, to my mind, black hole thermodynamics is incredibly rich even before one derives Hawking radiation. That's a fairly idiosyncratic view. I certainly don't think it's consensus. But I hope to have given a broad brush argument for it, and you can develop views on your own. But now let's get to quantum black holes proper. So I'm going to give a very brief introduction to Hawking radiation. I'm not going to do the derivation. I'm just going to sort of show you how it works. So the basic idea of, especially Hawking's original derivation, which I'll be doing here, is that there isn't going to be a unique particle interpretation for non-stationary spacetimes. And let me tell you what I mean by that. Here's how we would normally do QFT on a curved spacetime. So we start with our spacetime, mg, and let's say we have a massless complex scalar field. So massless complex valued scalar field phi, which satisfies the covariant wave equation. Like that. Okay. So normally anyone who's spent any time doing QFT knows that we choose our Hilbert space, technically our one particle structure, but that's a caveat, by defining the positive frequency solutions. And this is going to be really easy to do in stationary spacetimes, because they admit a time translation symmetry. So we define our time parameter with respect to our time translation symmetry, and then we define positive frequency with respect to that time parameter. So when we are in stationary spacetimes, we have a preferred particle interpretation given by the time translation symmetry. But in generic curved spacetimes, they're not going to be stationary. For example, if you have gravitational waves, you immediately have a non-stationary spacetime. And so there isn't going to be a unique global, a preferred global particle interpretation given by time translation symmetry. And this is going to lead to particle creation. So suppose I have a spacetime which I can divide into 3 regions. Call it M plus, M0, M minus. And let's say that the M plus region, not symmetry, stationary, is stationary, and the M minus region is stationary. But the M0 region is non-stationary, so it doesn't emit here a time-like Killing vector field. Therefore, we can have a particle interpretation here in M plus defined with respect to our time-like Killing vector field in this region, and a particle interpretation here. But there's going to be no unique particle interpretation, preferred particle interpretation in this region. And that's going to mean that the particle, if I put a state on this spacetime, so say the state omega, the number of particles that are in that state according to our particle interpretation in M minus is going to disagree with the number of particles according to our particle interpretation in M plus, because they're going to be different time-like Killing vector fields in those 2 regions. And so if we state that our omega is contains no particles for M minus, then we're going to have particles in M plus according to that particle interpretation. Then we will have a non-zero particle number in M plus. And so that's the basics of particle creation in curved spacetimes. This non-stationary region means that we don't have a global time-like Killing vector field, which is going to give rise to particle creation. So let's think about how this works for our black hole spacetime. So here is the conformal diagram for a short-shell black hole that forms from collapse, where this region behind the curvy line is the collapsed matter. Now on Scribe plus, the spacetime is stationary, and also on Scribe minus. And so we have a particle interpretation here and here. So now let's imagine a mode of our field which propagates from Scribe minus through the non-stationary region of the collapsing matter. Of course, it's collapsing matter, all sorts of stuff's going to be going on. It's going to be non-stationary here, and then propagates out to Scribe plus and is modeled here. What we're going to do is we're going to define a map between these modes. So you define a family of solutions in the past which are positive frequency with respect to the time translation symmetry on square minus. And you define a positive family of solutions to the wave equation on I plus. So you're going to be positive frequency with respect to the time translation symmetry there. So if we write down our covariant our field in terms of the creation and annihilation operators for our modes in the past, and then we're going to be able to write, excluding of course all the details, our modes on future null infinity in terms of these past modes, because our spacetime is globally hyperbolic, and so the past modes determine the future modes. Correspondingly, we can write the creation operator. So BI are the creation or the annihilation operators, and then there'll be corresponding creation operators in terms of the creation and annihilation operators for our modes on past null infinity. So if we stipulate that the state of our field is vacuum with respect to, I've put a minus if it's with respect to the modes defined on past null infinity, i.e. AI on our state was 0 for all I, then you can show that the number operator for modes in the future is equal to just the norm of our beta coefficients. And this will be non-zero. So our expected number of particles for this state, according to our particle interpretation on future null infinity, is going to be non-zero and given by this. And so we just need to determine these coefficients, and you get, this is what Hawking did, he determined these coefficients and got a particle number out. He did that exactly by trying to understand how a mode evolves. If you define it here, propagate it back along the horizon, and calculate what that mode looks like on past null infinity. And what you find is, of course, that at future null infinity, our state has a thermal spectrum at the Hawking temperature. TH equals kappa over 2 pi, where kappa is the surface gravity.
I missed one more thing, sorry. Am I audible?
Yeah, of course.
Yeah. So, like after the formation of black holes, like not all modes in future, past null infinity can be future, because some of modes may go inside the black hole near singularity inside. So those will not arrive future null infinity, and then I mean, how can we write all past modes in terms of future using this Bogoliova transformation? That I don't get.
So I've written future modes in terms of past modes, right?
Yeah.
So I haven't written past modes in terms of future modes.
So in past, there will be more modes.
Because look, I mean, I start with a mode up here, Pi, and whatever this looks like is going to be determined by a bunch of the modes on here, because our space-time is globally hyperbolic. Yes, you're right. Lots of the modes are going to fall in, but then they're just not going to contribute to what this mode looks like.
Yeah.
And so I'll just have a contribution from the relevant modes, and that's what's going to give me this equation.
Okay. Okay.
Okay. Good. So that's the briefest possible primer on Hawking radiation for those who didn't attend the QFT on curved spacetime course. So now let's think about how we're going to model black hole evaporation. Hawking radiation can't just be said to be emitted normally from a black hole. You can't just say, we've calculated that the black hole is emitting radiation, therefore it's losing mass. Because no component of Hawking radiation can ever be in causal contact with the black hole. And this is super obvious from my diagram. It's all in the causal past of the black hole, not in the causal future of it. Because as soon as you interact with the black hole, then you can't escape from it. Right? This is the whole point. The causal future of a black hole is just the interior of the black hole. And so we have to be more careful. We also can't, the way we think that a black hole evaporates is the Hawking radiation back reacts on the metric, which leads the metric to change, and that changing metric looks like evaporation. However, we also can't calculate the back reaction of the Hawking radiation on the space-time because we don't have a good quantum theory of gravity to analyze how that works. So instead what we do is we observe that in the exterior of the black hole, there is a time translation symmetry. Let me do a heading, black hole evaporation. Time translation symmetry, which is going to imply a conservation law. So we have a conservation law. And then we put basically a two-sphere around the black hole and observe, and using various approximation regimes, we know that there's an energy flux over through our tube surface. We then infer by our conservation law. So this implies a conservation law. We then infer that there's a negative energy flux going down over the horizon. So you have a negative energy flux now crossing the horizon, and we deduce then that the black hole loses mass energy due to that negative energy flux. So let's be a little bit more careful about how we do this. Our first job is to define our energy flux, which we can't do any more rigorously than defining an expected energy flux. Now, defining this quantity is very non-trivial in curved spacetimes. Again, people who came to the QFT on curved spacetime course would have seen some of this. But in a general curved spacetime, there's no preferred vacuum state. And anyway, we'd expect that the curvature of the spacetime to polarize the vacuum. And such we don't expect a trivial vacuum state in curved spacetimes. And hence, the usual normal ordering procedure of subtracting the vacuum energy to renormalize our stress energy tensor isn't going to work here because we don't have a well-defined vacuum energy. The way we do this in the end is we demand, I mean, this is, again, very much a superficial sketch. We demand that some quantity, for it to be this, to be the expected stress energy tensor, obey four conditions. The first is, I'll state it, but I certainly won't say what it means because we haven't done any of the stuff necessary to understand it, but just for completeness, this quantity is given by what's called a point splitting prescription. whenever this quantity, so that's psi x prime minus psi x prime, the first on a state omega 1 and omega 2, whenever that is a smooth function. Two is a much more easy to state. I mean, I'm stating heuristic versions of these, but the second is that our expression for the expected stress energy is fixed by the local, so this is the locality condition, the local space-time and quantum state. Three, for all states, for omega. The divergence is 0, so that's a conservation law, and in Minkowski space-time, our expected stress energy is 0. So I mean, I'm not going to use these again in the lecture, just to give you a flavor of like how we do it. We then prove that there's a quantity which obeys all of these, and it exists and it's unique. And so we proceed to use it. If you're interested in how this all works, look at Wald 1995, I think. The little red book, the QFT on curved space-time book. Okay, that was a little tangent to note that there's a lot of subtlety that goes into writing down what I'm now going to write down, which is that we define an expected energy current. JA is defined by the contraction of our expected stress energy with our time-like Killing vector field outside the collapsing matter. So this is our energy current. And this is conserved. So the divergence of J is just given by nabla A acting on TAB, and then times the Killing vector field and nabla A acting on a Killing vector field. This is 0 because we've demanded that it's 0. And this is 0 because it's an anti-symmetric thing by Killing's equation contracting it with a symmetric thing. And so we know, so we have a conservation law, and we have a time-like Killing vector field. We have our conserved quantity on it. And we know there's a positive expected energy flux because of Hawking's calculation. And so we infer a negative energy flux down towards the horizon. And thus we infer that the black hole is both radiating and will be losing mass energy. By dimensional analysis, we know that the power of the black hole is going to be proportional to 1 over m squared, where alpha is a dimensionless constant. So our job really is just to approximate alpha. And we're going to do that by modeling the black hole as a normal black body radiator. So the Stefan Boltzmann power law for a normal black body, power according to Stefan Boltzmann, is sigma A T to the 4, where sigma is the Stefan Boltzmann constant. A is the area of the black body. and T is the temperature. So using the Hawking temperature, TH equals 1 over 8 pi m, I've used it in terms of m instead of kappa, and the effective area of the black hole, which is, I mean, the simple way to think about it is, it's the area at which the wave radiation comes away from the black hole starts to look like a black body radiating. So it no longer looks like, so the light bending due to the gravitational field near the event horizon is no longer having a significant effect. Thus, to a reasonable approximation, alpha is 9 over, but just plugging in these numbers, 20,480 pi, where we've used in natural units, sigma is pi squared over 60. Natural units is everything's equal to 1. C equals G equals H bar equals Boltzmann's constant equal 1. Thus, we know the rate of change of mass but is going to be given by minus the power being emitted by it, which of course is going to be minus alpha over m squared. Integrating this gives, and this is obviously very standard integration, the mass as a function of time is the initial mass minus 3 alpha t to the power of a third, where m naught is the initial mass of the black hole. Thus, a black hole is expected to totally evaporate in finite time, specifically capital T now being time it takes for the black hole to completely evaporate is m naught cubed over 3 alpha. So plugging some numbers in. For a solar mass black hole, this time is approximately 2 times 10 to the 66 seconds, or about 10 to the 50 times the current age of the universe. So the time scales involved here are astonishing. For a primordial black hole that may be formed in the at the start of our universe, for it to have evaporated by now, so 14 billion years later, assuming it didn't absorb anything else, of course, it would have had to have been about 1 times 10 to about 10 to the 11 kilograms, which is about the combined weight of all living humans, which may seem like a lot, but is obviously really not very much at all. And it's got 14 billion years, so the rates of evaporation is incredibly slow. Of course, these are incredibly rough models and are expected to break down very seriously for a black hole of Planck mass. So really, we don't know that black holes evaporate completely, as I've said here.
Excuse
me. Yeah.
Sorry, so we can say that after the Big Bang, we don't have any evaporation of the black hole, according to this number of that you mentioned. So it's a very long time, yes?
The time for a black hole to evaporate is an incredibly long time. Now, of course, you could write down a model in which your black hole mass is infinitesimal, and then it won't be the age of the lifetime of the universe to evaporate. So there can be different models, but yeah, it's about as slow as a process can get, the time for a black hole to evaporate. You need an incredibly incredibly low mass black hole for it to have anything like a reasonable time of evaporating before it eats anything else and goes larger, right? I mean, the Hawking temperature is much, much, much colder than the cosmic microwave background. So if you took a black hole sitting in the cosmic microwave background, it's going to be getting larger because it's going to be eating the cosmic microwave background energy, which is more energetic than the Hawking radiation it's going to be emitting. And so yeah, we don't expect black holes to be evaporating particularly often.
Well, thank you very much.
So I'm going to indulge myself again and just talk about a note of caution on modeling black hole evaporation. And this is just a nice way to emphasize the need for negative energy flux. Black hole. So let's say we model Hawking radiation with the classical stress energy tensor, T mu nu. And so we're modeling Hawking radiation, N nu Fm over R squared, where N nu is the outward pointing null vector. R is the normal radial Schwarzschild distance, and Fm is some function, some mass-dependent term, which we don't bother fixing. Okay. Now, a spherically symmetric solution to Einstein's equations with this stress energy tensor is the Weiergeometric. ds squared is 1 minus Tmu over R du squared minus du dr plus R squared d omega squared, where 2mu is some non-increasing function of retarded time u minus t, u equals t minus r. You can also have it, the Weiergeometric for Tmu being non-decreasing, in which case rather than having a radiative model, you have a collapsing model. That's how collapse is often, the collapse of stars can be modeled. But when it's non-increasing, the picture you should have is of a star with a field of radiation heading outwards. And then where that radiation has currently got to, beyond that, it's just normal Schwarzschild. So the radiation just looks like a contribution to the mass term in a Schwarzschild black hole. So using this metric, we can compute the connection coefficients, and we find that the Ricci tensor is given by 2m over r squared dmu over du delta 0 mu delta 0 nu. And so the Ricci scalar is just the contraction, which is the inverse 0, 0 component of the metric, which is 0. Because there's no RR component in the normal metric, so the inverse metric has no 0, 0 component. Hence the Einstein equation gives T mu nu is equal to minus 4 pi over R squared dmu over du delta 0 mu, delta 0 nu, which is the stress energy tensor of the radiating field under the geometric optics approximation. The same things come out. So now using this, we can model the energy density measured locally by an observer moving on a world line with full velocity given by ui. So just the full velocity is measured by the retarded time coordinate. Basically following the radiation out away from the star. The energy density is T mu nu, u mu u nu is -1 over 4 pi r squared dmu du. And so this is super easy to read. As the black hole, as the body is radiating, it loses mass. And this radiation propagates in a sphere of radius r. And because we defined our mu function as a non-increasing function of u, we have epsilon is positive semi-definite, i.e., the weak energy condition is satisfied. T mu nu is v nu greater than 0 for any causal vector, v. And so this is looking very much like a normal classical model of radiation. Remember, classical models of radiation are going to obey our energy condition. So we can fix very easily, we can fix mu such that it looks like the black body is radiating at the Hawking temperature. So we've got a nice Hawking temperature model of radiation. Can this model black hole radiation? And importantly, it can't. And let's look at why. So if we draw the Penrose diagram for a radiating star, we're going to have the star, and as it radiates, it's going to disappear. And eventually, there's going to be no star left at R0. It's going to radiate away all of its energy. So up here, it's Minkowski. And the radiation is going to head out to infinity along here, along these sorts of lines. And so if you imagine an observer in this exterior region, but when it gets the energy here, it's going to think that the star has a particular mass. Let's call it m. And when it gets a bit more radiation, it's going to think the star has a bit less mass, m minus delta m. So m minus delta m. And between large quantities of radiation being emitted, it's going to look like the star has a basically approximately stationary mass. And so these regions are going to be approximately isometric to a region of Schwarzschild, of collapsed Schwarzschild, because it's going to look like the star has a stationary mass, as in the Schwarzschild case. But in our picture of Hawking radiation, we can even, I'll talk about the evaporation in a sec. We can't model in the same way we did here. The radiation comes from the matter, because as discussed, then it would never escape to the black hole. So radiation's got to come from this sort of region out to infinity, and this sort of region. And so we have to have a negative energy flux going over the horizon. And so now we've got this very different structure. This is going to be our region. Approximately isometric to a region of Schwarzschild, which clearly has a different structure to these regions. And so these can't be identified. And so we know we've got to be doing something more sophisticated than just using a non-increasing radiative biogeometric to model black hole radiation. Finally, now drawing these diagrams, I'll just note that if we expect a black hole to evaporate completely and disappear, then in this diagram, we have the black hole continuing forever to time like infinity. But now we think it's going to be shrinking. So we get rid of this. We instead have a point or region, sorry, at which these are terrible lines. The space-time looks Minkowski again. So a observer up here, so this is R0 equals 0 again. Here we have R equals 0, square plus, square minus. Up here, space-time looks Minkowski again, and down here it looks like an evaporating black hole. One thing to note about this version of modeling black hole evaporation is this point here is a naked singularity. And so on this model, anything can escape from that black hole, a photon can escape from the black hole. Therefore, this space-time is no longer globally hyperbolic. Most physicists expect this naked singularity and the singularity in general to be resolved in a theory of quantum gravity, and they expect to get deterministic evolution back through the evaporation event. But in this, the most standard model of black hole evaporation in the semi-classical limit that we have a breakdown of global hyperbolicity, which one sees as a problem until it has a resolution. Okay, good. I don't have much more to say except to go even more superficial and point out some nice features of using black holes as thermodynamic bodies once we have Hawking radiation. So, black holes, thermodynamic objects. Okay. So, like with all thermodynamic objects, our black hole is going to have a heat capacity. Now, if you throw some heat, some energy into a black hole in the form of radiation, then its mass increases, and so the Hawking temperature decreases. And so the specific heat capacity is given by T ds by dt, which for black hole, for Schwarzschild black hole, is given by 8 pi over t squared, which is going to be negative. And so black holes have Schwarzschild black holes, I should say. Sorry. Schwarzschild black holes have negative heat capacity. Now, negative specific heat capacity is a typical property of a self-gravitating system. It's known that for a collection of bodies acting under Newtonian gravity, as a particle loses potential energy, it falls towards the center of mass and its kinetic energy increases. Therefore, just acting under self-gravity, a Newtonian system increases the energy of all the particles, and therefore its temperature without bound. So it's got no final thermal equilibrium state that it reaches. And this keeps happening until quantum or relativistic physics takes over and it becomes a black hole, or there's some sort of quantum interaction that happens. And so that's fairly normal. One of the really nice things about black holes is the complexity of the heat capacity once we start considering Kerr or Kerr-Newman black holes. Everything I'm about to say again applies to the charged case in terms of the electric potential and the charge of the black hole, but again, as usual, I'll just treat the rotational case. Paul Davies showed in, I think, what year was that? In 1977, checking my notes, that for a Kerr black hole of constant angular velocity, so omega is constant, then the specific heat, then the heat capacity, not the specific heat capacity, is always negative. So we still have this always negative result, as in the Schwarzschild case. However, the heat capacity at constant angular momentum, if we now allow ourselves to vary the angular velocity but keep the angular momentum constant, then it's not true that this is always negative. In fact, it's got a super interesting behavior. If on the y-axis, we plot the heat capacity, on the z-axis, we plot angular momentum over m squared, then the heat capacity starts in negative and gets increasingly negative and blows up to negative infinity, beyond which point it's infinitely positive and then returns to a maximal value. No, it returns to zero, sorry, at a maximum for a critical Kerr black hole. And so what you see here in the heat capacity behavior of the black hole is phase structure. You have a phase transition at this point in the phase space from a negative heat capacity object to a positive heat capacity object. And phase transitions are another classic instance of property of thermodynamic systems. So as just discussed, black holes can have complicated phase structure. Another famous example, a super early one of this, was what's called the Hawking-Page transition, which is a transition that black holes undergo in asymptotically anti-de Sitter, when embedded in asymptotically anti-de Sitter spaces. But as we haven't discussed anti-de Sitter spacetime at all, I won't talk about that, but I'll talk about a different phase transition, which was proved by Carlip and Weiger, which is super similar. So now, for a charged, let's call this the Carlip-Weiger transition. I might just talk about it, actually. So for a charged asymptotically flat black hole, so it's not asymptotically anti-de Sitter anymore, it's asymptotically flat. There's a phase transition such that below the Hawking temperature, below a critical temperature, sorry, this region, a black hole is an unstable configuration. You can't have a black hole and a thermal bath which are in equilibrium with each other. So the black hole's radiating, the thermal bath is thermal radiation is being absorbed into a black hole, and these are in equilibrium. That's an unstable configuration. But then above the critical temperature, the black hole is a stable state, and it can be in thermal equilibrium with the radiation, where equilibrium requires a finite cavity for us to keep the radiation in, which contains the black hole. And so you have this phase transition from a black hole being an unstable configuration to a black hole being thermodynamically preferable. And so we have thermal equilibrium, we have thermodynamically preferable states, and we have phase transitions. All of which is just sort of giving a picture of a really rich world of when we treat black holes as thermal bodies. And finally, to finish these lectures off, I want to show how treating black holes is. I take an example from a review article by Carlip, which is really nice. And it's just a nice, fun thing for us to finish on. A way we can learn about future physics from black hole thermodynamics. Or how even black hole thermodynamics constrains future physics. So instead of imagining that all particles have a universal speed limit, which is the speed of light, imagine there are two distinct species of particles, A and B, which each have their own maximum speed limits, CB and CA, such that the maximum speed limit of CB particles is larger than that for CA particles. Now, if this were true, you can use a black hole to build a perpetual motion machine. Let's see how that works. The event horizon for particles, for CA particles, will be outside that of CB particles, because CB particles can travel faster, and so they can escape stronger gravitational potentials. So the horizon for B particles is inside that for A particles. And that means that the Hawking temperature for A particles, let's say AH for A on the horizon, is going to be less than that than for TB particles, because of course for smaller horizons we have larger Hawking temperatures. So we have TBH is larger than TAH. Now we're going to build two heat baths to connect thermally, to connect to these two horizons. And we're going to have one heat bath which only interacts with particles of species A, and another which only interacts with particles of species B, so B bath. And we're going to arrange the temperatures in the following way. We know that the horizon for the Hawking temperature for B particles is greater than that for A particles. We're also going to make it greater than the thermal bath, which interacts with the B particles. It's going to be greater than the temperature of the thermal bath, which interacts with A particles. It's going to be greater than the temperature of the horizon for A particles. Now this inequality, because the bath is at a larger temperature than the horizon, means that there'll be a flux of energy from species A heat bath into the black hole. So the black hole is going to have more mass due to these species A particles. The first inequality implies that there's going to be a flux from the black hole to the B bath, because the Hawking temperature for the B bath, for the B horizon, is larger than that for the B bath. So there's always a flux from higher temperature to lower temperature. So there's a flux from the A bath into the black hole, and the flux from the black hole into the B bath. And so we can rig the temperatures so that the flux into the black hole balances out the flux out. So the black hole size and the mass and the temperature remain constant. But that means that we're getting a flux from the A bath, total energy flux from the A bath into the B bath. And so we're extracting energy from a colder heat bath into a hotter heat bath, which violates the second law of thermodynamics in various formulations. And so if we impose the second form of second law of thermodynamics on black holes in the I think it's the Kelvin form. Someone correct me if I'm wrong. In the Kelvin form, then we rule out two different possibilities. So possibilities where we have two different speed limits for two different types of particles. Now this is quite a weak argument, right? Like it's just a fun example. And you can't conclude from this that future physics must be Lorentz invariant or violate the second law, because you can have other ways of being Lorentz invariant. Like you could be Lorentz invariant in this two speed limit and have a universal speed limit. But it's just nice to see how black hole thermodynamics can connect to these really core ideas in our physical theorizing. Okay. Let me stop sharing. That's all I have for you today. Are there any questions?
Excuse me.
Oh, yeah.
Can we say that the singularity follows the physical law? For example, in a evaporating, because if the singularity doesn't follow the physical laws, we have a different manner. So, whole the corp of the black hole include the singularity following the physical law or not? Thank you very much.
So we have to be careful what we mean by a singularity. A singularity really is not an object or a thing. It's how we describe our space-time structure breaking down. And so there aren't space-time points which correspond to the singularity. There's just no, the manifold isn't there. It's outside our physical descriptions. There are no sort of laws of physics which apply to the singularity because they're not part of our physical description. The way we identify singularities is we take our future and extendable curves and we see how they behave. We see if all of our future and extendable curves are complete. And if they're not, we say, well, this curve can't go any further, but it's not complete, so something's stopping it. Our manifold must be stopping. And so we say that at that point there's a singularity. But they're not part of the structure of our theory, i.e. a manifold of beautivometric or some sort of quantum field, which allows us to apply physical descriptions to them. Now, when we get a theory of quantum gravity, most people expect what's called singularity resolution, which is whatever is out there in the world, which we're currently modeling with singularities and general relativity, we'll get a model which is apt to description in our quantum theory of gravity. But by the standards of current physics, they're just not describable. And so we identify them sort of through these like other ways, i.e. inextendable, incomplete curves. Any other questions? The last chance, it's the last lecture. Okay, I guess we can wrap up there then. I mean, I'm inclined to hand it back to Bruno, see if he has anything concluding he wants to say, or anything administrative that needs to happen before we wrap up.
I just think we have to say thank you to a couple of people. So I'm saying in your behalf as well. So thank you to the other organizers. That's Caio, Nick, and Rafael. Our Zoom room is a courtesy of the Department of Mathematical Physics from Universidade de São Paulo. So we thank them as well. And above all, thank you for you, the audience, who has been engaging and endured 6 lectures, and maybe even people from the future, people watching us on YouTube in the future. Thank you for for our patience as well. Yeah, that's all I had. Yeah.
Yeah, I concur. Thanks very much, everyone. Thanks for your attention. Okay.
That's it. Bye.